Okay, so we'll talk about the classical theory of the firm. If you think of modern firms, there are, of course, many different kinds of firms. But the typical firms that we think about, Apple, Microsoft, Ford Motor Company, and organizations like that, Reliance Industries, these are massive firms, right? Very large organizations with often thousands of workers and a complex internal hierarchy, and so on. So before we set out on laying out the mathematical model for the classical theory of the firm, let's take a step back and try to understand the overall nature of this theory and the sort of implicit assumptions that go into it. So of course, the starting assumption of this classical theory is that the objective of firms is to maximize profits. Now, you can obviously very easily think of exceptions. Please mute yourselves, guys. Somansh, please mute yourself.
One nice thing about India.
I am already muted. Maybe someone else have joined through my
Somebody has their microphone on. Please switch it off.
His mic is on.
And there are certainly two people in Pakistan who love them as well. And I'm one of those people as well. India and Pakistan, two countries that have fought multiple wars. What do you think would happen if you went to Pakistan?
Sorry.
Guys, I mean, you have to be absolutely careful that you don't unmute yourself accidentally. It just causes enormous disruption to the class. Okay. Let me share screen again. All right. So we can obviously think of these exceptions to the profit maximization principle. There are firms, for example, in India, we have several large PSUs, public sector undertakings, Indian Oil, till very lately Air India. Of course, that has been sold to the Tatas. But, BSNL and firms like that, Indian Railways, yeah. Can you hear me, guys? Am I
Yes, sir.
Yes, sir.
Yes, sir.
So those don't come under this kind of analysis. Then there are NGOs, non-profit organizations. A leading example would be some microfinance institutions, right, who are relatively big players. They give out a large volume of loans, but their objective is to alleviate poverty, subject to, breaking even, and so on. And then there are things like vanity projects, for example, IPL teams. It's not obvious at all that their owners want to maximize profits. Maybe they want to maximize trophies or glory or something like that. So having said that, I think in a modern capitalist economy, it's not a bad starting assumption to say that your typical firm is a profit maximizer. So moving on, another issue, again, we'll not explore any of these points in depth, but if you take courses in, say, industrial organization or contract theory and courses like that in your second year, there's a whole bunch of optionals which will give you an opportunity to explore some of these points I'm mentioning in much greater depth. But let me nevertheless just draw your attention to them at this point. So here's another point, and this point was first made by Ronald Coase. Ronald Coase pointed out that, the way decisions are made and resources are allocated within a firm resembles socialism, resembles a planned economy. So the CEO or the CFO and other top officials determine which division should get how much resources, for example, between the R&D division, the manufacturing division, the marketing division, how should the firm's outlay be divided. So that's not determined by a price system. The price system operates in terms of exchange and resource allocation across firms. But within a firm, we almost have a socialist planned economy, so to speak. These days, corporate practice sometimes tries to bring in the price mechanism within the firm or voting mechanisms. There's, some decisions are determined by kind of crowdsourcing, if you will. The employees may vote or put in their inputs to decide which division should get how much money. So these are sort of more recent advances, but by and large, within firms, you have a top-down planned system. So the question which Coase raised is that, we have a capitalist price-based system, but we have these socialist islands which are participating in the price-based market economy. So what determines the boundary? Yeah, for example, if you take the auto industry, the American auto industry is much more inclined towards in-house production. So even the small components like the rear view mirrors or the leather seats, they'll be produced in-house. Whereas the Japanese auto industry, companies like Honda and Toyota and companies like that, they often do a lot of outsourcing. So the small parts, they'll make the big parts like the engine themselves, but the smaller components are often purchased from other companies and through the market. Yeah. So in some sense, as far as the auto industry is concerned, in Japan, the socialist islands are smaller and they're trading with each other. In America, the socialist island is bigger. So what determines the boundary is a question, and the broad answer that Coase and his followers provided is transaction costs. Right? That's a big black box, but you can open it up. Another important issue is, which is extremely relevant for modern day capitalist societies, is the following. There's a separation of ownership and management. If you go back to the early days, when sort of modern industrial economies were taking off in Britain and then in other countries, the firm was a much smaller entity. Often it would be a privately held proprietorship. So for example, take a little grocery store where the owner is there and maybe has a hired employee. So it's largely managed and even serviced by the owner of the firm. That's a very different situation from a company like Microsoft, for example, right? Where who are the owners? They're the shareholders, but the shareholders have absolutely no participation in the day-to-day decision-making of the company. They may attend an annual meeting where they may express some broad views, but there's an obvious separation between ownership, management, and labor, right? You can think of it as a triad. So owners in modern corporations, especially the ones which are publicly listed, the owners, the shareholders, they have to constantly worry whether, for example, the management is working in their interest or they're pursuing goals of their own. So this gives rise to what is called agency problems, that the owner is not running the firm, somebody else is running it on the owner's behalf. So how can the owner align the interests, his own interests and the manager's interests to the extent possible? And that's where you have disciplines like corporate finance and organizational theory and contract theory. Essentially, the idea is that you have to structure the compensation of the employee, of the manager, let's say, so that their interests largely coincide with that of the owners. For example, if they're paid largely in stock options. Then when the company does well and its value increases, the manager also gets higher pay, and that may bring the interests of the two parties closer together. Although such devices like paying the manager not a flat salary, but paying in terms of stock options, that has some negative effects, which a lot of papers explore. For example, the manager may take some gimmicky actions which fool the market into driving up the stock prices in the short run, but in the long run, the value of the company may go down. Okay, so that's another thing to keep in mind. We'll ignore these things. I'm just putting little flags over here as things to think about. These issues are swept on the carpet under the simple classical approach we are going to take. The last thing is, often profit maximization is a dynamic problem. Firms may face situations where, to increase their long-run profits, they may want to sacrifice some short-run profits. That can happen in many ways, but one possibility is from competition. So there may be trade-offs between profit maximization in the short run and the long run. So for example, you have, let's say Indigo is a dominant player in the airline market, and suppose there are new airlines coming in and competing with them on the busy, profitable sectors like Delhi, Mumbai. One strategy that firms sometimes adopt in these situations is called predatory pricing. They price even below their cost. They take on losses themselves, but with the hope that the rival will be driven out of the market. In order to compete, they'll have to match these low prices, and that'll inflict losses on both sides. And the incumbent firm, if it's big and powerful and has deep pockets and long credit lines, they hope to sort of ride out this loss-making phase and drive up the rival, and then go back to charging higher prices again. Of course, some of these strategies are against the law. They run into competition law or antitrust laws, but it's a cat and mouse game, right? Whether authorities can catch this sort of practice is another matter. Anyway, the bottom line is that although the problem, the model will study formulates profit maximization as a one-time problem, right? A static problem. In the real world, there's complicated dynamic elements to profit maximization. Okay. Very quickly, any questions? All right, let me move forward and sketch out the classical model for you. I'm not going to spend too much time on production theory because there's a lot of overlap with consumer theory or demand theory. Up to a certain point, it's essentially identical, and then there's a little bit extra over here. So we'll cover this one relatively quickly. So the model says that let's look at a firm. The firm produces, let's say, one output. The analysis can be extended to multi-product firms very easily. But let's assume one output measured by Y. And the firm can produce it using n different inputs like labor, capital, energy, raw materials, and so on. So this is the vector of inputs, right? N different inputs. Now, the first thing we need to know to do the analysis is what is the input-output relationship? What combination of inputs can produce how much output? And in most production processes, there will be some flexibility. You can generate the same output of a good or service in relatively labor-intensive ways, let's say, or in more capital-intensive ways. So for example, if it's a firm which makes cloth and garments, they can adopt more sort of household kind of technology. Like, for example, some of our traditional weaving industry, in Benares or Ludhiana, they're doing much more handicraft-based production of saris and other garments. But then there's more machine-based, sort of mass-produced garments, where capital is the factor which is relied on more heavily. So the production function. So what the starting point will be what is called the production function. It's a relationship between inputs and output. So for every input vector, the production function f tells you how much output will be produced. We'll assume that f is continuous, strictly increasing. Of course, if you have more inputs, you can't produce less output. And strictly quasi-concave. So like the utility function, our production function is quasi-concave. With f0 equal to 0. No inputs means no output. As I said earlier at some point, the production function has to be thought of as a cardinal function. For the utility function, in the modern ordinal approach, we saw that we can take, for example, a log transformation or any increasing monotone transformation of the utility function. It continues to be a valid utility function, capturing the same preferences. That is not true in the theory of the firm, right? The value of the production function has an absolute significance. So if it says that with 1,000 workers and $10 million worth of capital, a firm can produce 500 cars, then that 500 number cannot be changed by taking log transformation or anything. 500 cars is 500 cars. It has objective, measurable significance. Okay, so we can define an isoquant, right? It is the exact correspondence of the indifference curve. What is an indifference curve? It's the set of consumption vectors which produce the same utility. An isoquant is the set of input vectors which produce the same output. Okay, it's exactly mathematically analogous to the indifference curve. It's just, you can take the same mathematical object and call it by different names, and you go from the indifference curve to the isoquant. So, and as you remember, when we assume that the utility function is quasi-concave, that implied that indifference curves are convex. Similarly over here, since we are assuming that the production function is quasi-concave, that means our isoquants will be convex shaped. Now, one feature of the production function which is important is the idea of returns to scale. Okay, so let's define what that is. Returns to scale measures what happens when you scale up inputs. Okay, so let's think of increasing inputs by the same proportion. So you double the amount of labor, the amount of capital, and the amount of energy used. Let's say all the inputs are doubled. Of course, output will go up but the question is by a factor of 2 or more or less. Okay, depending on the answer to that, we'll call the production function as having constant returns to scale or decreasing or increasing returns to scale. So constant returns to scale is when, if you increase all inputs by the same factor lambda, then output also goes up by exactly the lambda factor. Okay, if it goes by less than lambda, then we have DRS. If it goes up by more than lambda, we have increasing returns to scale. Now, in principle, a production function can have different properties at different points. I'm coming to the questions. It can have different properties, right? So in some region, it can have increasing returns. In other regions, it can have decreasing returns. Nothing stops us. Nothing stops a production process from having that kind of feature. But let's restrict our attention at this point to what is called homogeneous production functions. All right. So what does that mean? That means its returns to scale feature holds at every point. Wherever you start in terms of an input vector, you get the same property everywhere. Mathematically speaking, we'll think of homogeneous production functions. So what are those objects? A production function is homogeneous of degree k if for every input vector, you have this relationship that if you multiply all inputs by lambda, then your output goes up by the factor lambda to the power k, right? Where k is some constant. Okay. Now, this constant is the degree of homogeneity of the production function. And you can easily relate it to the definitions of CRS, DRS, right? The value of k determines whether this homogeneous production function has CRS, DRS, or IRS. That's very easy to see, right? And there's nothing really to prove here. So for example, if k equal to 1, then it immediately fits the definition of constant returns to scale. If k is greater than 1, that means that if you double inputs, for example, output will go up by a factor more than 2. So that's the case of increasing returns to scale. Yes, Shaunak.
Sir, am I audible now?
Yes.
So can you please go to the previous slide, like when it's written the. So can you please see? So I understand what's constant returns to scale. Can you please explain with example like decreasing and increasing? Because what I want to understand is, say I have a factory and I increase. I make another factory which is just the same. So it's like mimicking the first one. So the number of outputs should be doubled. Like if I'm having another factory, like I can mimic.
So your question is, why can't firms simply clone their production processes, right? They're producing 1,000 cars using some process. All they can do is just essentially clone it, build a plant.
Yes, that will essentially
right.
Like strike out the option of decreasing.
So let me explain, right? I summarized your question. So here's my reply, which is that one kind of response to that, why does, let's say, decreasing returns to scale happen if this kind of cloning is always possible? And one answer to that is that there are always, perhaps in the background, some factors of production, some inputs, which are held in fixed quantity, right? So for example, managerial attention, that after all, if you clone a factory and build a second factory exactly like that, it still has to be supervised, So if managerial attention is limited, then when you build a second factory, each factory will perhaps its performance will come down a little, because the manager is now struggling to manage both of these things and do timely sort of orders. Firefighting, if some problem breaks out, tackling that. So managerial attention now gets thinned across the two factories. So that's one way to think about why decreasing returns to scale might happen. Yeah.
Thank you, sir. It's clear now.
Nilava.
Sir, in our model, which one of these returns to scale will you assume? That means in our model, our firms will be constant returns to scale.
I will not assume anything. I'm just defining these features, and I'll allow for all three possibilities.
Okay, thank you.
All right, so let's now focus on the profit maximization problem. We'll assume to start with a perfectly competitive market. One of the things, of course, one of the lessons as you go through studying microeconomics is that this assumption matters a lot. If you have imperfect competition, if the assumption of price-taking behavior by firms is not true in some market, then results fundamentally change. For example, the first welfare theorem could break down. So if you have the other extreme end is monopoly. That's a market where there's a single firm, and of course that firm won't behave in a price-taking manner. We'll study monopoly. That's the next topic coming up, and you'll see in monopoly that inefficiencies and deadweight losses crop up, right? And in the next course, you'll study oligopoly, where there's a small number of firms which are strategically interacting with each other. And many of the oligopoly models, like the Kuno model, for example, which you'll study using game theory, you'll see that the same feature obtains. Anyway, as the starting point of the study of firms, we'll assume a perfectly competitive market whose crux is that each firm acts as a price taker, takes the market price as given. And the market price not only of output, but also on all the inputs that it uses. So the firm faces from the market these parameters, the price of the output P and the vector of input prices, which we'll call W. Yes, it goes from W1 to Wn. So what is the firm's problem? The firm's problem is to maximize the difference between revenue and all the money it spends on purchasing these inputs from the market. Okay, so that's the Wx thing. So this difference by definition is profits. And the firm is choosing this. And what is the constraint on the firm? The constraint on the firm is the production function. The output cannot exceed what is permitted by the production function. And the production function essentially captures the technology which the firm has, right? If the firm somehow finds new, better methods of producing, for example, if it's finds a better technology, then its production function will change, and that will change the firm's profit maximization problem. But at a given point in time, there's a given technology which is captured by the production function. So this is the constraint, and it's very easy to see, just like in the consumer's problem, for profit maximization, this constraint will actually bind. Yes, y is equal to fx. You don't want to produce 1,000 cars and throw away or destroy 100 of them and sell only 900. You want to sell everything that you have produced. So this, without any loss of generality, becomes an equality constraint. And then one way to try and solve this problem is to do just the substitution. Instead of y, we can just throw in the production function. And so our maximization problem can be defined in terms of choosing an input vector. If we know the production function, the moment we choose an input vector, we have essentially also chosen the output level. Okay, so the firm is solving this unconstrained maximization problem. Now, there's another approach to try and solve this problem, which is a two-step approach. Okay, and there are some advantages of doing it. So let's discuss this two-step solution to the profit maximization problem of the firm. So the first step is to construct what is called a cost function. Okay, in this step, let's arbitrarily fix some output target, y. Okay, for some reason, the firm has decided that it wants to manufacture 1,000 cars, and it has to decide, should it rely more on robots and automated assembly lines, or should it rely more on people, workers? So the firm solves the cost minimization problem in this first stage, which is minimize the total expenditure on inputs subject to meeting your output target. Yes. And once you solve that problem, the value function of that problem is what is called the cost function. Yes. So the cost function is the value function of the cost minimization problem given an output target. Carefully notice what are the arguments of the cost function. Of course, the prices of the various inputs will affect the cost function. Okay. And also the output target itself. If we want to produce 2,000 cars instead of 1,000, that'll of course change the cost you have to incur. So this is the cost function. Now, once we have derived it, we can go to the second stage, and we can now, as a last step, we can do the profit maximization exercise. And here, the problem will be simple. There will be no constraints. Essentially, the question will be what volume of output ends up maximizing the profit of the firm, provided any output is produced in a cost minimizing way, right? So that's the last step of this two-step approach. Now, what is the advantage of the two-step approach? The advantage is that the first step is already known to us, those of us who have studied choice theory, consumer theory. This problem is essentially the dual of the consumer's problem. Yes. Remember, the consumer's primal problem is utility maximization given a budget. The dual of that was given a utility target, some utility that we have to achieve for this consumer. What is the least costly way of achieving that? That gave us the expenditure function. Now, the cost function is essentially the expenditure function, isn't it? If we call the utility function a production function and solve this problem, we are exactly doing the dual problem of the consumer. So what we got out of that, namely the expenditure function, we're just calling it by a different name here. We're calling it a cost function. So everything we learned about the expenditure function, for example, that it's concave in the prices, can be straightforwardly brought in over here. That's the advantage of breaking it up into these two steps. And you know, when we solve this cost minimization problem, we get conditional input demand functions, conditional on an output target. How much of each input will the firm demand from the input markets? Those are the exact analog of the Hicksian demand functions. Yes. So everything we learned about the Hicksian demand function, for example, what is one thing we learned?
So it's a choice function of the dual problem of a consumer.
One property of the Hicksian demand function. Can you name a property that we derived?
A law of demand.
Sir, it is homogeneous of degrees.
Yeah, homogeneous of degree 0. And somebody mentioned law of demand, right? Law of demand applies to Hicksian demand functions. They are necessarily downward sloping in own price. So that property we can again extend here without a thought, right? So these conditional input demand functions will be downward sloping in the own price. So if you fix the output target of a firm, and if labor becomes more expensive, for sure they'll cut down on their labor force. Yeah, that we can say. All right, Rishi.
So can the Shepherd's lemma also be applied here?
Yeah, absolutely. Everything. All I'm saying is, you know, that these are identical. The cost function is just the expenditure function by another name. So its mathematical properties are identical to that of the expenditure function. Yes.
So in the first part, if we have fixed the level of production of Y, then why are we maximizing with respect to it in the second part?
Because ultimately we're interested in profit maximization. Yes.
So first we fix the Y and get an X as a function of Y, and then we fluctuate Y to get the maximum value.
So first we figure out for any arbitrary output level, what is the cost minimizing way of producing it. Having solved that problem, we now ask the question, what output level will maximize profits?
But the output level X, like if we take an inputs of X, like sir, at production of Y, if the cost is minimum, then the product profit is maximum, right? At that point only.
I'm not sure what you're asking. So
in the first,
the firm has to.
Okay, sir.
A firm has to. What is the firm's problem? What does the CEO of the firm have to decide on? He has to decide on how many people to hire, how much capital to buy, and whatever other inputs, and then how many cars to sell. Okay. Now,
okay, sir.
One way for him to do it is to go to some engineer accountant team and say, look, I'll decide on the number of cars. Tell me what's the least cost way in which I can make 1 car, 2 cars, 3 cars, 1,000 cars, 10,000 cars. Just give me that relationship between my production target and how much it'll cost us. So they gave him a table which lists that. And then the CEO has to, of course, decide how many cars he wants to make for the company. At the end of the day, he has to make a firm decision.
Yes, sir. Yes, sir.
So, yeah. Stuti.
Sir, my doubt is similar to Rishi's doubt. So, sir, first part we are minimizing cost.
Yeah.
In the second part, we are maximizing profit. So,
Okay.
sir, isn't minimizing cost dual of maximizing profit?
No, it's not. Why will it be?
Sir, because if whether we minimize the cost or maximize the profit, I think we will get the
So
same.
not. Cost is one component of profit. There's the other side of profit, which is revenue. So why will the one be the dual of the other? Cost minimization is a subset of the overall profit maximization problem. A firm which does not minimize costs is not maximizing profits, for sure. If you have failed to do cost minimization, then you can stick to the same number of same volume of output and just produce it in a different way so that costs come down. But that does not mean that you have maximized profits. Maybe there's further scope for increasing your profits by moving to a higher or lower volume of production. Profit is revenue minus cost. So if you cost minimization is necessary for profit maximization, but certainly not sufficient. Why is it sufficient?
And sir, if we are maximizing profit, does it imply that we will be minimizing cost?
Profit maximization implies cost minimization, but cost minimization does not imply profit maximization. It's a one-way implication.
All right, sir. All right. Thank you, sir.
So since we are taking price as a constant, aren't the two same? Cost minimization and profit maximization.
No, I'm not sure why this confusion is arising.
So it should be dual of maximum revenue or maximum production, right? Instead of profit maximization, the cost minimization part.
That's right. Okay, so that's a nice way of putting it. Yeah, I should have said that. Okay, since you're bringing the concept of a dual, what is the dual of the cost minimization problem? The dual of the cost minimization problem, remember what dual is, right? Dual means that, we flip the objective function and the constraint function. We flip them around and change minimum to maximum and maximum to minimum, etc. So the dual of this problem of cost minimization is output maximization for a given budget. For some reason, the firm has a fixed amount of money it can use to purchase inputs, and it spends that money to maximize output. That is the dual of the problem. It's output maximization for a given budget. It's not profit maximization. Right?
Sir, can we please go back to the previous slide?
Yeah.
Sir, in the second point, P is the output price and W is the input price vector, right?
That's right.
So I think you've written it the other way around in point 2 of the slide.
Okay. Yeah.
Yes, sir.
So this is output price. Sorry about that. These typos are very difficult to, almost like viruses. This should be output price and this should be input prices. Yeah. Yeah.
Sir, in profit maximization, we used to differentiate by quantity in order, like we used to find the maximum output which firm should produce. Sir, so revenue maximization, like when objective function is to maximize revenue, will that be analogous to profit maximization problem?
No, why will it be analogous to profit maximization? Profit is revenue minus cost.
Right, sir.
So if you only want to maximize the revenue part, in fact, if you take the prices given, maximizing revenue has no finite solution. You produce as much as you can, right? If you're going to ignore the cost of production, if you, for whatever reason, you want to maximize revenue, there's no finite answer to that.
Yes, sir, got it. So, sir, profit maximization problem is completely different and is not linked to the dual.
Yeah.
Thank you, sir.
Yeah. Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay. Very quickly, Kanishk.
Sir, output, maximizing output given an expenditure is the dual of cost function.
Is the dual problem of the cost minimization problem.
Sir, how is the expenditure coming if we do not know the output?
How does expenditure coming? I mean,
It's a function of Q bar, right? We are assuming it to be equal to f of x is equal to say y. So it will be a function of y, right?
Okay, so it's not P. Okay, so it's a money income, not output times price.
Yeah, exactly.
Okay,
So
okay.
it's a parameter. So
okay, so let me just be painfully explicit here. Let's go back to the
No, but it's equal to output, right?
Let me just give it 2 minutes and see if any confusion remains. Okay.
So it's given in this.
Give it 2 minutes, guys. I mean, okay, so let's go back to the consumer's problem. Okay, what is the original consumer's problem? Maximize utility subject to px y minus px equal to 0. All right. What is the dual of the consumer's problem? This is the constraint function gx. Right?
Minimize it with subject to constant utility.
Yeah. So, well, let me write it this way, just to be absolutely sure there's no confusion. Okay, so let's say, let me write it like px minus y equals 0. All right. What is a dual? We switch the objective function and the constraint function. So this comes here. Px minus y. So when we minimize it, we are essentially, y is a constant. So I won't write that. So px minus y, minimize that. Both cases by choosing x, subject to ux equal to some value u. That value is whatever the maximized value of utility was in the first problem. Okay. So that's the structure. So these are the two dual problems. Now I can say, all right, instead of this function u, I'll call it f. This vector p, call it a vector w. This constant u, I'll call it another number y. Right? And this thing which I was calling y, I'll call it whatever, some expenditure level E. So what do I get? I get this problem just by changing names. I have basically defined the firm's cost minimization problem. Right? So just if you just look at this, you will see all the analogies that you want to think about. Srota.
Sir, but won't we maximize the profits in the firm's problem? Here we are maximizing the FX, the output.
I'm not sure why all
excuse me.
If I just redefine things like this way, right? You agree that this is the firm's cost minimization problem. Okay. Now, what is the dual of this? The dual of this, in the consumer's case, was the utility maximization problem. Here, just by using the new labels, we get the dual of this is maximize output subject to a given expenditure outlay of the firm. The dual of this is not the cost.
I got it. Sir. Yeah, got it.
Okay, I have to move on really. I really want to finish this today. So I'll hold off on questions for a moment, for some time. All right, so now let's focus on the cost minimization problem. Okay. And at least for homogeneous production functions, let's ask the question, can we say something about the nature of the cost curve, the shape of the cost curve, in particular, its curvature properties, if we know the corresponding shapes of the production function? So if the production function is, let's say, concave, what will be the shape of the cost function? And the answer to that is that there's a very close link. And for homogeneous production functions, this is the theorem or the result which tells you what the link is. So let's think of a production function which is homogeneous of degree k. Yes. Then the cost function takes this form. It's some constant times y raised to the power 1 over k. So for example, if k is less than 1, we have a decreasing returns to scale production function. That means the production function is concave. That means the cost function will be convex. It will have the opposite curvature. And the same kind of link exists between the production function and the input demand functions. The input demand for this production function can also be written as some constant times y to the power 1 over k. So if the degree of homogeneity of the production function is, let's say, 3, if it's IRS, right, then our cost and input demand functions will be concave, y raised to the power 1 over 3. And in the intermediate case, where k equal to 1, we have constant returns to scale. Then the cost and input demand functions are linear. Yes. So this is a useful property. And let me discuss on the next slide, sketch the proof for this. The proof is quite easy and short. But let's discuss yeah, I'll come back and take questions. Just hold up. Let me finish this proof, and then I'll open it up. Okay, so why am I making this claim on the previous side, right? Well, let's look at the cost function. Okay, it's the value function of the cost minimization problem by definition. So it's the minimized cost for a given output target for every given input price vector. Okay. Now we can fiddle around with the objective functions and the constraint functions in permissible ways to get from here to the last line. Okay. So what are we doing in the second step? What I'm doing is, in the objective function, I am multiplying by y to the power 1 over k, as well as dividing, right? So I'm taking this input vector x and multiplying it by this scalar, but then I'm also I'm multiplying by y minus 1 over k, but I'm also multiplying by its reciprocal on the outside. So these two things cancel out. So minimizing wx is the same as this object. And on the side of the constraint, I'm taking the y to the other side, essentially. Is 1 over y, right? So I have preserved the objective function and the constraint really through this manipulation. Okay, then we go to the third step. The third step, this is all right. So now what I want to do is I want to take this coefficient inside the function. And that's where the homogeneity comes in useful. From the definition of the function being homogeneous of degree k, this object and this object are the same. Yes. If I take x and multiply it by y to the power minus 1 over k, and if I take it outside, by the definition of homogeneous functions, when it goes outside, it gets raised to the power k. And so the 1 over k and the k cancels out, and you are left with y to the power 1 minus 1. Okay, so the jump from the second line to the third line is absolutely valid. Okay, and now if you look at, now suppose we redefine the vector, instead of x, let's call it z. Okay, what is z? Z is just this, the vector x multiplied by this scalar. Okay, so here we have minimize wz, and here also inside the production function we have the same thing sitting, so we'll just call it z. Okay, so then we get to the fourth line. And now if you look closely to the fourth line, if you forget this coefficient, right, just suppress it for a moment, minimize wz subject to fz equal to 1 is basically the cost minimization problem with an output target of 1. Okay, so that gives us the value of the cost function when output target is 1. But of course, there's this coefficient sitting here, so in the end we have to multiply it by that. So that takes us to the last line. Okay, so that's a proof of this relationship. It's pretty easy to understand. So for example, you start with some input vector, and the firm is making 1,000 cars. For the same input vector, suppose the firm wants to double its output. Okay. Now, since the input prices haven't changed, yes, that means that the firm will use the same input ratios for homogeneous production functions if it wants to scale up its output. So if it wants to produce 2,000 cars, it'll use inputs in the same proportion, right? That's something that you can prove. So if it has, let's say, decreasing returns to scale, then to double its output, it has to more than double the inputs, okay? And that's why its cost will more than double. So that's the broad intuition. Okay, Kanishk.
Sir, my hand was up. I'm sorry.
Okay, Antora. Antora, you have a question? Maybe that's an error. Okay, so now let's go back to the second.
Sir, I have a question.
Yes.
Sir, in the there's a word multiplicatively separable. What does mean? Yes, sir.
It means that in general, it's a function of these two things, the input price vector and the output level. And it takes the form that two things are multiplied with each other. The first thing only contains W, and the second thing only contains Y.
Okay, sir. Thank you.
Some function of W is multiplied by some function of Y to give you the cost function. For example, if the cost function was this term plus C plus Y, then it wouldn't be multiplicatively separable.
Okay, sir. Okay. Thank you.
Vishal.
Yes, sir. Sir, I have doubt in next.
Yeah.
I want to clarify one thing, that due to homogeneous, we have written y power -1 fx same as fy power -1 by kx, that function.
Yes. From here to there, it's using the fact that the function is homogeneous.
Okay, sir.
All right. So now look at the second stage of our profit maximization, right? So solving this problem. Here, there's no constraint in the first place, and there's only one thing being chosen, Y, output level. So first, for ETA solutions, first derivative equal to 0, which means price minus the derivative of the cost function, which is the marginal cost derivative with respect to y. So this is the classic profit maximization principle, that the firm should carry on production up to the point where price and marginal cost are equal. If it's producing less than that, so price is, let's say, greater than marginal cost, that means if it produces one extra unit, then price is what the extra revenue that it will bring in, and the marginal cost is the extra cost of producing that unit. So if there's a gap between the two, there's a scope for increasing profits by expanding production. And if the gap between the two is the other way around, price is less than marginal cost, then by the same token, the firm can increase its profits by cutting down on production. Right? So standard marginal reasoning that we have seen several times by now. But of course, second order condition has to be satisfied. Yeah. So the second derivative of this has to be negative. And since the first term is linear, the second derivative is essentially the negative of the second derivative of the cost function. So that term has to be negative, which means at the optimum point, marginal cost should be increasing, or the second derivative of the cost function should be positive. Okay, so that's our second order condition. We need at the optimum point increasing marginal cost feature. And here's where we run into a bit of a conundrum. If the technology is increasing returns to scale everywhere, then the second order condition will never be satisfied at any point where price equals marginal cost, right? Increasing returns to scale means, based on what we proved in the previous slide. So if K, let's say it's a homogeneous production function, increasing returns means K is greater than 1, which means our cost function is convex in Y, right? Because 1 by K is a number bigger than 1. So if it's convex, that means its second derivative is positive everywhere. So, sorry,
But the production function is convex, so the cost function will be concave.
It's concave, right?
Yes.
Concave everywhere, which means you won't be able to satisfy the second order condition, right? And that's very easy to see in a picture. Let me pull up this. Sticking to homogeneous production functions. If you have decreasing returns to scale, that means our marginal cost function is downward sloping. Sorry, IRS means it's downward sloping. Let me also draw the picture for, so this is for increasing returns to scale. This is for decreasing returns to scale. For decreasing returns, we have a positively sloped marginal cost curve. And if there's a market price, this point is the candidate for the optimum output, for the profit maximizing output level, right? X star. And indeed, it is profit maximizing in this picture because this area captures the profit. The first unit produced fetches this price, but costs less as given by the marginal cost curve. So this gap is the profit on the first unit. This gap is the profit on the second unit. This is the profit on the third unit. If we add all of them up, we get this area, and that's the total profit. And no other production level can give a higher profit. So things are fine here. In the case of increasing returns to scale, yes, this is a candidate, but if we end up choosing this, we'll end up minimizing profit rather than maximizing profit, or rather we'll maximize losses, because as you can see from the picture, the first unit actually costs more to produce than the price. Second unit costs the same feature. So all these vertical distances are really losses rather than profits. So if I choose this point in this picture, then I have maximized losses, not profits. What is the optimum choice in this picture?
Sir, infinite production.
Infinite. As you go beyond X star, your cost keeps falling, but the market price is the same. So all this area becomes profit, and this area is basically infinite. So you would like to produce an infinite, either an infinite quantity or a zero quantity. One situation would be that this is the market price, and the marginal cost curve is declining, but it remains above the market price everywhere. And here, of course, the optimal choice is zero. So when there's increasing returns and the firm is acting in a price-taking manner, or we assume that the firm is acting in a price-taking manner, its optimum output is either zero or infinity. Okay, and infinity will not be compatible with, of course, market equilibrium. So, so we reach a situation that for firms with increasing returns, the model doesn't quite close, right? Each firm would like to produce either nothing or infinity. So you can't find the market equilibrium.
Sir, in case of constant returns to scale, our cost function is going to be linear. So therefore, the marginal cost is going to be
I'm coming to the
horizontal. All right, sir. It's going to be constant. All right. Thank you.
So the thing is, so what happens if you have a perfectly competitive market on IRS, right? The model won't close. You won't get a nice market clearing price where each firm is producing some finite quantity. Well, the thing is, when you have increasing returns is not compatible with perfect competition. Increasing returns leads to what is called natural monopolies, right? Essentially, a firm which is very big and has more market share than its rivals is in a position to charge a low price and still be profitable, okay? So it can drive out its rivals by charging a low price. So the market will soon come to be dominated by a single firm. So this is the case. So IRS tends to lead to a monopoly. Sometimes monopolies are created by laws, for example, patent and copyright laws, right? It protects the market for one firm. But in these situations, the natural competition leads to monopolies. So IRS tends to monopolies. So when we are studying perfectly competitive markets, we will have to assume that there cannot be increasing returns to scale everywhere throughout the output range, right? There may be initially increasing returns to scale, but eventually some form of decreasing returns has to set in. Let's look at the borderline case of constant returns to scale. There, the marginal cost is constant, right? From the formula that we derived a couple of slides back. So if this is the market price, then this is the let's say the marginal cost. Okay. In this case, obviously, the optimal choice of the firm is zero. The other alternative is this is the market price, and marginal cost is below that. Here, the optimal choice of the firm is
Infinite.
Infinity. Okay. Here's one situation where there's a so let's say this is the marginal cost. I'm just randomly assigning colors. Bear with me. And suppose the market price is the same. I'm drawing it slightly above to distinguish, but basically market price coincides with the marginal cost of each firm. Then the firm is indifferent between any output levels, right? Anything from 0 to infinity is optimum. So any finite amount is also optimum. So essentially, when all firms have the same marginal cost, let's say, and they're all constant returns, then the market supply curve will end up being horizontal at that common marginal cost of all the firms. At this price, they are indifferent between supplying any quantity. At any lower price, they will supply zero. So you could just as well draw this. And any price above this, all of them wants to supply infinity. So if you have a market demand curve in that case, like this, it intersects the supply curve at some point, and it gives an aggregate market quantity, equilibrium market quantity. Now, how much each firm will produce, that's indeterminate. We cannot solve it within the model. But this is a perfectly logical, internally consistent market equilibrium when we have global constant returns to scale. Okay, so bottom line is that for technologies which have decreasing returns to scale or even constant returns to scale, we can have a perfectly competitive market. We can solve for market equilibrium. We can, there's no internal logical problem. When there's global increasing returns to scale or even increasing returns to scale up to a very large volume of output, then the market cannot remain perfectly competitive. It has to somehow devolve into a monopoly, which we'll call a natural monopoly. Any questions, guys? There were some hands raised.
So could you explain the last diagram?
Yeah. Okay. The last diagram, which one? This one. Yeah.
Yes, sir.
This one. So I'm talking about a case where all firms have the same production function, let's say, and that production function has constant returns to scale. As we discussed earlier, that gives rise to a cost function for each firm, which is essentially linear, right? It's some constant times output. So each firm has the same marginal cost, regardless of how much they're producing. So what I said is that in that case, the supply curve in the market will be horizontal at that marginal cost, which is common to all firms. Because at that marginal cost, as we discussed in the two previous pictures I drew, firms are willing to supply any amount. Below that, they won't supply anything. Above that, they want to supply, sky high, infinity. So the supply curve becomes like this. And then if you know where the demand curve is, what the demand function is, you can solve for the intersection. And you can say, using our market model, that this is the aggregate quantity that will be produced by the market. If somebody asks you how much will each firm produce, you won't be able to answer that, right? This Q star can be supplied by different firms in different ways. Maybe one firm produces more than another. We can't predict that within the model. But what we can say using our model of competitive markets is that aggregate supply will be this specific number, nothing else. Okay, so
Got it, sir. Thank you.
Okay, guys, can I take 10 extra minutes? Can I prolong the class by 10 extra minutes? I wanted to finish this.
So we have other classes.
We have a class. Sir, we have tutorials right now.
Oh God. Is there a time slot where I can just do an extra bit today?
So we have a class with Sugata sir at 8 in the evening as well.
Yes, sir.
Is there no free time at all?
Not today. We
So
have
at least not today.
Yeah. So we have back-to-back classes till 4 and then 8 to 10.
After 4?
Sir, lunch.
Well.
So can we have it tomorrow at 12:55?
Well, that's the problem. I don't have. I won't be able to take it for tomorrow, day after. I have to travel a bit. Maybe for the rest of it, I'll just make a little recorded video and put it up. Okay. And then I can take your questions later if you have any. So what remains to be discussed is the sort of, the same kind of question we asked for the demand function, that what are the testable implications? For example, can we state some sort of a law of supply that if the market price goes up, the firm will supply more output? So there are a few slides where we derive those properties. So I'll record that part and put it up there. Yeah.
Okay, sir. Sir,
Sir, if people are willing, there are I think only three tunes for now.